Okay, I'm going to do that annoying playing with the lights thing. Nope, that was the wrong one. Sorry, wrong one. Okay. I just want to turn off the one in front of the screen. That's the one you generally want. That's also not that helpful. Okay, we're going to try the third and final option, see if we like it better. Oh, that's where we started with. Okay, so I guess this is how our lights are. Great. Okay, if you can see, today we're going to start our regular practice of doing a little poll everywhere warm-up at the beginning, but we just talked about syllabus on Wednesday, so the poll everywhere today is just tell me why you're in this class, and then we'll all see why we're all here together. You know, shared experiences matter. So I'm somewhat assuming you're familiar with poll everywhere, but please go to this link. Can somebody give me a thumbs up if you can actually enter it? Like, is it live? Thank you. Appreciate you. Okay, so take a few minutes, do that, get settled, and then, yeah, we've got stuff to actually learn today. Exciting. All right. Okay, now I am going to take a look at our poll everywhere. Let's see how things are shaken out. Okay, so why are you taking this course? What terrible contrast. I apologize. So the question is, why are you here? All reasons are wonderfully valid. Let's see. To further my programming abilities. Okay, respect. I don't look at the names on these, so if this is for brownie points, that was a waste of your time, just so you know. But amazing. That's really exciting. Graduation requirement? Absolutely. Absolutely. Shout out to you. I understand. Let's see, to pass technical interviews, glad to hear it. We'll certainly talk plenty about it, and I'll probably post a lot of resources for you to sort of get started on that journey afterwards. But while I'm sort of vamping on this question right now, just an FYI, if you are interested in a job that requires a technical interview, most good recruiters will confirm that you've completed this course before you do any technical interviews, because data structures and algorithms is actually a very universal class, at least in sort of Western computing tradition. And though we don't all teach exactly the same thing, when engineers think about the questions they may ask you in a technical interview, they think about the content from this class primarily. So though not every single school teaches exactly the same topics, I can tell you I actually did a massive survey of like 50 CS departments across North America, and it is a surprisingly standardized set. So if you've been doing technical interviews already and not having a good time because you haven't taken this class, it's not your fault. You didn't learn that stuff yet. If you feel anxious and behind, don't worry. You can't really do anything in technical interviews yet until you pass this class. So those folks certainly are in the right place. Programming abilities, absolutely. Shout out to those gluttons. Appreciate you. I understand. Why would you take this 4-credit class? It's a 5. It's a 5. I'm sorry. It's like political reasons we can't make it a 5, but prepare yourselves. And shout out to those that just possibly wandered in here with no idea. Good for you. Does anyone know why they're anywhere? Thank you for sharing. Okay, cool. So now consider this. Theoretically, Poll Everywhere has some magical Canvas integration now. This is new to me. So I'm never going to look at your answers, but now you have all been recorded as having participated in some way. These Poll Everywhere questions I will leave up until the next lecture. So essentially at the beginning of each lecture, I'm going to go in and like hot swap the active one to the next one. So if you are watching this on the Panoptos, or you plan to watch these on Panoptos, you can still get your participation point, but you have to do it before the next lecture. That's my little carrot for staying in time with the course, if you will. And remember that this type of participation, if you participate, and I'll pick some threshold closer to the end of the quarter, like if you participate in like 85% or more of these polls, that gives me the freedom to round up your GPA at the end of the quarter. Because I can only use one significant digit in GPA, so give me the chance to maybe give you a little boost if I can. Okay, cool. It will remain active, so if you haven't, gotten your participation point, but wow, look, okay, 190 people. Good for y'all. There's definitely 300 something people in this class, supposedly, but this looks like a really full room. Can 300 fit in this room? I don't know where the rest of y'all are. Okay, anyway. So what are we doing today? Oh, announcements, really important. Okay, thank you all for your infinite patience. I know the class website isn't posted yet. It's my fault, it's me. Because you know that thing you do where you're like, my programming assignment is almost done. I just gotta do that final build, and that'll be like so fast, right? Listen, we all fall for that. It was not fast. It's been 3 days, okay? But me and 3 other professors are currently debugging this ridiculous template, and I swear it will be live later today, which is perfect because we are also going to post your first programming assignment later today as well. This programming assignment is the one that will be individual. I am also going to be frank with you. It is significantly less conceptually and programmatically complex than the other ones. Because the point of this is to give you an opportunity to set up your laptop with Java and IntelliJ, get used to pulling things locally from GitLab, all of that good stuff, all the systems, and it contains a collection of sort of small bite-sized problems I literally borrowed from 143 back in the day that I think are a good representation of the skills you want to carry forward with you from the intro series. So if you're in this room and you're like, my Java's really rusty, or I took the intro series somewhere else and I don't know if I'm quite ready for this class, if you do this homework and you're like, ooh, that was deeply uncomfortable, that should be a sign to you that maybe it's going to be even more uncomfortable going forward. Does anybody have any questions, administratively or about any of the stuff I just rattled off? Cool. I will make an ed post when everything is actually live, which I will end this class and go do. And so in order to assist you in this homework assignment, our office hours are going to officially start next week. The TAs sort of pick the times that they're available. So unlike intro, we don't have like those big blocks. We don't have 100 TAs to staff an IPL. So you will need to look at the calendar to figure out when a TA is available, and they will be at different locations. Most of them will be in the computer science buildings. So if you're not familiar, those two over there. But that website, or the website will have that calendar later. We'll be starting those on Monday. I also will be hosting drop-in office hours. I do also have my one-on-one sign-up office hours, which shout out to all of you. I already booked up for the first 2 weeks, so I'm gonna add more time on there. Let's talk. I wanna meet you. That's cool. Okay. Yes, please.
Is there anything we have to do on GitLab to join this class?
Oh, thank you. You do not have to initiate anything on GitLab. We have a GitLab with the starter code, and we will then hit some magic button and send you a GitLab repo tied to your UW-Net ID, and that's what's going to unblock you from getting started on the first assignment. Same thing, we'll make sure you're in the grade scope and all that good stuff. Cool. Okay. Oh, yes, please.
Are office hours walk-in, or do we have to set up an appointment?
Office hours are walk-in. The only things that are by appointment is my little bit.ly one, but I will have walk-in office hours as well. So come, do your homework there, make friends, the usual. Okay, cool. All right. So what are we here to learn? What's this class about? Oh, that's so funny. Sorry. This is the old version of this slide I spent so lovingly updating, but now we're going to talk about it. So, okay. I know every professor says their class is like the most important class, but let me tell you why my class is the most important class, okay? So I am assuming you have all come out of some type of introductory series. It may have been 2 classes, it may have been 3, maybe you took 1 and here you are. But when I think of learning computer science in this way, it's really like learning a new language, because there's new vocabulary, there's new grammatical structures, there's new logic behind the way that you formulate your thoughts. And so we are following a pattern that you might follow picking up any foreign language, where before you can really get into it, you kind of have to have some vocab. So I think of like CS121, CS142, that's vocab. You're just learning like what are some of those keywords? Can you type them exactly without missing those annoying semicolons and curly braces? Can you just sort of take instructions and then repeat them? The next level, once you kind of have some of the words, is to start to use some of the more complicated structures. We call this being a client of perhaps some objects. So maybe you used existing objects like scanner or the file input output, or you're using an array. You didn't build those things, you are using them. So those are things that are in your toolbox already made for you, and you are using in the ways that have been set out to do for you. So I sort of think of that as like learning grammar and sentence structure. You're starting to combine those key words to make more complicated phrases. But ultimately, it's not super creative yet. It's still about the building blocks of how this language is going to communicate your ideas to the computer. And then you show up here, and Casey stops showing you code in lecture. I teach you no more syntax because I totally inappropriately assume that you just know it all. You can Google it. It's fine. That's what we all do. But this class, I assume that you know the basics of what these types of programming languages Java can do. And this is all about creativity. How can we take these tools that we've learned to use in the most direct ways and recombine them and assess how to recombine them in the most optimal way for what we decide is our priority? And as it turns out, there's not usually a single right answer. In fact, I love if somebody can find a better answer than the one that I come up with, and if you can argue it against me, listen, I'm a nerd. If you are technically right, that is my favorite kind of right. So as long as you can justify it, as long as your creativity has truly expressed your idea in code, you are going to be successful in this class. And that is also why this class is sort of the final piece of foundation in learning how to code. You've been learning it all probably in one language, Java. That's how we do it here at the University of Washington. And then after this class, you'll notice that a bunch more classes become available to you, 417, 410, 414, things like that. And that's where you start to get into more of the specialization. And so a lot of folks at this point, they ask me, what's the difference between, say, an electrical and computing engineering degree and a software degree if I were to go into industry? Well, the reality is, after this course, you are at the same foundational level as a CS major. But the difference is, after this, what different types of specialities you go into and how many different specialities and how many different patterns you find to use the things we learn in this class. So that is the reason why a lot of recruiters will ask, have you taken data structures and algorithms before they consider you for an interview? Because also that typically is the foundational level of information you need before you can say, contribute to a large code repository and be functional as an intern. Now, a lot of companies, they will not care what language you learned it in, because languages have a lot of similarities in the things they're able to do. They might just have different vocab or slightly different grammar structures for how you go about accomplishing the same type of logic. Some do it more elegantly than others. Some are better suited to different types of problems than others are. But once you learn the whole pathway in one language, then it's about repeating problems in different technologies so you can start to see the patterns across technologies. But that's for your next professor. We're just all about learning to write poetry in this class. Annoying? Yes. Okay, let's go. So this class is called Data Structures and Algorithms. So here is what Casey decided are some high-level definitions. These are not official by any means. So a data structure is just a way of taking multiple pieces of data and structuring them together based on how those things are related or how you want to use them. So a good example is an array. A variable in Java is a singular data point, right? If you have int x equals 4, that's a singular point. But if you have an array of ints, you can have multiple numbers all collected together. They all have indices. They're in a linear format. That is starting to establish a relationship across multiple pieces of data. And in that case, maybe because you want to store them in an order, or you want to, dive in and get something from a specific index at the middle or at the end, or whatever your purpose is. In this class, we're going to start to learn a lot more complicated ways to string related pieces of information together. And sometimes those pieces of information won't even all be of the same type. And just to mess with your brains, sometimes those collections will be of collections. If I had an array of arrays, that's a two-dimensional array. But you could have a linked list of arrays. You could have a linked list of binary trees. We are going to figure out how to combine these different structures of data to accomplish what your targeted goal is. And that goal might be reducing memory. It might be quick lookup. It might be, adding and removing things. It changes based on the scenario. An algorithm, that is just a series of precise instructions. I like to think of it as a recipe. When I teach this in high school, I literally have a cookie recipe. In the intro series, you may have picked some algorithms up, things like binary search. I think of that as the phone book search, which maybe dates me. But if you were going to look up something in the phone book, you probably look in the middle first, and then look if the name you're looking for is to the left or the right of it, and then you kind of split in half. There's kind of a procedural way of going about finding that information that you're looking for. In this class, I'm going to teach you a bunch more convoluted ways to navigate these super convoluted data structures to find what you're looking for. So data structures and algorithms is all about collecting together data at a scale you probably have not experienced so far and applying algorithms on top of it to efficiently answer the questions you're trying to answer. Because computers are really good at scale, they're really good at data, they're really good at following precise instructions, but they are terrible at interpretation. So your job is to design how you communicate to the computer as optimally as possible for what it's good at so that you can accomplish what you're good at, which is the interpretation. Okay, these are some review things. I'm not going to go too deep into Java review, but remember that at least in Java, Java is an object-oriented language. And what that means is that you have sort of two fundamental categories of code files. First, you have what we might refer to as the client class. That's typically the one with the main method in it. That's the one that when you tell the computer run or execute, that's the one file that it's going to go and execute. And it's going to look at the instructions and go from the top to the bottom. But those instructions will probably leverage a bunch of different tools that have different abilities and different ways to store information inside of them and give you information about that data. Those are something we're going to refer to as objects. In the 1-2x series, 122 is a lot about being a client of objects, and then 123 is about starting to write your own objects. So I do assume that you already know how to write your own objects, but this class is going to be all about how we really design and nest objects within one another. Great. Okay. Now, let's talk about this magic thing called the ADT. Okay, also, sorry, I totally forgot. I put a thread on the ed board, which you can find a link to from the Canvas. And that thread is where you can ask any questions about this lecture as we go throughout. And usually I'll have that thread up in case, I want to go and you want to ask a question digitally, or you want to go in there and upvote some questions. Also, usually our superstar TAs are in there answering questions as we go. So you are always welcome to raise a hand and interrupt me, but if you would rather do it digitally, there is an ed thread under lectures with the same title as this lecture. You're welcome to ask questions there as well. Okay, so what is this thing called the ADT? ADT stands for Abstract Data Type, and it is essentially a culturally agreed upon set of behaviors for a data structure or a collection of information. Because it turns out there's actually a lot of ways to physically tell the computer how to store, say, linear data all in a row. But we needed a way to sort of abstract out what is the specific dynamic, what's the relationship, what are the functionalities we need out of a structure. And then once we really isolate what our goals are, that gives us the opportunity to go in and decide what's the optimal implementation. So this is a level of abstraction that just talks about how that structure is going to behave, not about how you're going to write the code for it. And shout out, it was invented by Barbara Liskov, who actually was the keynote at CSE's graduation last year, because I got to tell her she was in my slides. So it's really about starting to think of code at scale. Before this, everybody just wrote really long files, and we didn't really get to reuse a lot of code, and we didn't really know what everyone's data structure is, and she saw these patterns, and she said, hey, I see a lot of people implementing something that kind of looks similar. Let's standardize on what this structure is supposed to do so we can abstract out the functionality from the implementation so that we can optimize for both. And this is a big part of this class. I'm going to first ask you in any design, what is the functionality you're trying to optimize for? What is the thing you think the user is going to do the most often? What is the one thing that if it happened would break your code, so we have to prevent that from ever happening? Or what is the one thing that needs to be so optimized because it happens all the time? That's more ADT. Then we can talk about what pieces of code you write in order to accomplish that. So here is an ADT you may be familiar with. It is called the list. In intro, we still do linked int list, or we do linked int, what is it? Linked int list. We have a bunch of like intro specific ones, and I can't always remember what their names are. But the list ADT is this idea of a collection of pieces of the same type of data that are in a linear form, and they contain, or they are associated with indices. So they each have their own sort of sub-address within the grand thing. I kind of think of it as like an apartment block, and then there's like apartment numbers. Like where are you in the specific structure of related things? But what we know about the list ADT is that we need to be able to insert things in the middle, and if I do that, everything shifts. I need to be able to change things, add things, remove things. All of those things are functionality. Notice how, as I was describing that, not once did I mention anything you could actually turn into code. I didn't say the word array. I didn't say node, anything like that. So now what we're going to talk about is this functionality and the two different ways you could implement it and why, in some situations, one might be better versus the other. Okay. Related to ADTs, this is a Java-specific thing. You may remember this idea of something called an interface. An interface in Java is literally just a name and then a bunch of method headers. But what that means philosophically is a name and a set of behaviors. Because what is a method header other than sort of your agreement with whoever is using that method of what comes in and what goes out? So an interface is a collection of different methods with names that take in something and or return something, and that collection gives you some sort of overall functionality. So you might have encountered the comparable interface. The comparable interface is one that says, whatever data structure implements me, then I must have a method compare to that will tell you numerically two items of the same type, which one comes first in order. So, if it's numbers, maybe it's numerical order. If it's the alphabet, it's maybe alphabetic order, so on and so forth. But that's an example of an interface. It's an idea of how in Java code we would articulate functionality independent of implementation. So you have already kind of been using this. We just probably didn't call it an ADT at the time. Okay, so here, just to give you some specific example, we talked about the list. Here is the code to actually define the list ADT. So it's called list. It takes in, and for reference, if you're not familiar with this is an angular bracket, an uppercase E and an angular bracket. This is something we are going to call generics. that E is just sort of like a placeholder for element. So what this means is a list of elements, a list of things. You might even sometimes see the word T used in its place of E. And so you can see what this means is that we have this set of method headers. We have get that takes in an index, which will always be a number, and then returns back whatever type of element is stored at that index. So that's one functionality we know the list needs to make available to us. It's the get functionality. Give me what apartment number, I'll tell you who lives there. Then we have set, we take in the element to put into the list, and we take in the index where it's supposed to be, we override that. Append, that means however many things are in the list, add something to the end, which means that the list grows in size. Now you might have encountered the array list in intro. That is using an array to implement this functionality. And if you remember, arrays are static size. So you have to do some kind of funky stuff in order to make it so that the arrays can pretend as if you could just add infinitely, and we're going to talk about that. But that's just one possible implementation. Okay. Here are some other ADTs that you've also kind of already seen. So lists, maybe you saw the array list. Stack, we're going to talk more about stacks, queues, and maps on Monday. Stack is that first in, first out order. The queue is first in, last out order. The queue is the first in, first out. I think of the stack as like, and I'm sorry if this is sort of like US centric, but in schools, when they have those lunch trays, they're always in that sort of like well with a spring. And whenever the fresh ones come out, they're always wet and they like push them on top. And the ones on the bottom are all gunky and weird, and they're always like, something's down there because nobody gets to the bottom very often, but you always have a wet tray because it's always the first one the lunch lady puts on top. That's a stack, right? A queue, that's a line at a bank, at least a polite line at a bank. If you get there first, hopefully the teller serves you first. And then a map, that is where we actually have two pieces of information associated with one another. It is often called a dictionary. So in a dictionary, you would have the word and the definition. Those are two separate pieces of information that are associated as a single entry. That's a map. And throughout this course, we're going to be talking about a lot of different ways to implement these, especially the dictionary. We're particularly obsessed with dictionary. Okay, this is, now that we've sort of had this colloquial conversation about it, some more formal definitions of these things. I put these in the slides. If you're that type of person, you're welcome to read them, but pretty much just a repeat of what I said. Here's our other loose analogy. So an ADT is describing the functionality, so maybe the functionality you need is some mode of transportation. You must be able to move, and hopefully you have control over where that thing moves. That would be helpful. But there are a lot of ways to accomplish that. So the data structures that would implement that ADT, maybe a car, that's one way to move and steer, different from how an airplane or a bicycle would accomplish the same general ideas, but you can imagine different scenarios in which each one of these would be more optimal. If you're going next door, probably not going to take an airplane. If you're going across the country, probably not going to take a bicycle, unless you are that person, and then shout out to you. Okay, so here returning, array int list. Thanks, past Casey. She knew she was going to forget the name of this. Array int list is what you might have implemented in intro. So here is a actual implementation of the list ADT using an underlying array. This one is specifically only for things of type int. That's because in intro they didn't want to make you deal with this generics thing. Guess what? In all of your programming assignments, you're going to have to use generics. But Casey, nobody taught us how to use generics. I know, somebody should really get on that. I'll post some resources. Welcome to Stack Overflow. It is an important skill. But you can see here what we've got is that, remember, this is what we're asking the list to be able to do. In order to accomplish that with an array, we need an array as an underlying structure to hold a collection of elements. And then we're going to add another piece of information, a size. Because remember, the array can't grow. So what I'm going to do is I'm going to pick an array of a certain size because I have to make an array of some size. So like, let's say my default size is 10. Before I put anything into the list, that size is 0, but I have a capacity for 10 items. And now since I have these two separate pieces of information, I can much more easily mimic the list behavior because I know if my current size is less than my capacity, then I can just keep adding to the end or inserting, no problem. But if I have a size equal to capacity, that means I've run out of space of my underlying array, and that means I need to make a new array and copy things over and move it all over, blah, blah, blah. But we're going to do that as developers here in 373, and the person who's using your wonderful thing, they don't need to worry about that. They don't need to worry about the copying over. They just know, they say add it to the list and it gets added. So we're separating out the implementation from the functionality. Great. Okay. Here's some of them. Again, just a preview of things that we'll see throughout the quarter. We are going to get into some deeper ones. You can look at these for funsies. Okay, talked for a while. Any questions so far or ideas? Yes, please.
Is zero indexing for like accessing elements of this part of the abstract data type of the list?
Ooh, good question. So if you do not recall, in computer science, we use 0 as the first number from which we count, historical reasons. And in the list, yes, we will always assume 0-based indexing, which means the very first or leftmost element will always be stored at index 0. And whatever extra space we have will probably be at the later part of the array. It also means that the last element in the array is always at capacity minus 1. So you got to go do that little off by 1 adjustment. But yes, we do assume 0-based indexing for lists. Yes. Yes.
In this class, are we going to be using interfaces or are we just implementing the data structures?
Yes to both. You will both use interfaces. You will use many data structures. You will write your own data structures. I'm not going to make you write your own interface, but you will have to use them. Okay. Let's dig into this implementation in a little more detail. So again, here's our sort of picture. Here's what it might look like in actual code, where we have an array list. So that's an ADT implemented by the data structure array. We have the names collection. That is an instance of this particular data structure. And we would call methods on it using that dot operator, and then we pass things in for parameters. I know that's review, but I also know a bunch of you haven't touched code in a year plus. Cool. Okay. So let's talk about how these things are implemented. So we've talked a lot about the array list implementation, because I think that's the one you are likely familiar with from intro. But what's another way we could accomplish this? Well, linked lists, which is a collection of objects that reference one another, is another way to simulate this linear structure of data, but it has some trade-offs. So let's look at some animations. Let's say we call insert on these two different implementations of the list ADT. In the array list, I've got an underlying array with a capacity of 4. It's currently got a size of 3. So that means this bucket over here is just sort of waiting for another item to be appended. If I call insert of the value 10 at index 0, what that means is I want 10 to eventually be discoverable under this index 0, which means 3, 4, and 5 have to bump to the right. So I'm going to copy from the back, I'm going to copy 5 into that empty space, because you always move into the empty space first because you're not going to lose anything, right? So you move things into places where you're not going to lose anything. Now we have 2 5s, so I'm going to replace one of those 5s with a 4. Now I have 2 4s. I'm going to replace one of those 4s with a 3. Now I have 2 3s. I can finally replace that with a 10. So I have done this sort of shifting within the internal array so that the ultimate result is that 10 is at 0, but the other things remain in the same relative order. All that shifting and stuff, though, keep that in mind, because that is instructions in a loop that we're going to have to consider as sort of a cost anytime we do this. Now, a linked list, these are how I'm going to represent nodes, which are just independent objects. The arrows are what we're going to refer to as references. We're We're going to talk in a lot more detail about what that means, but essentially it's just a fancy way of saying each of these objects has the address in memory for where to find the next object. But that's it. They don't know about who comes before them. They don't know about who comes to after them. They just know who comes next. But what's really nice about that, it's very likely me. Gosh, you don't turn off your phone one time. Oh, okay. I thought it was LA Fitness because I've been dodging that payday. Sorry, LA Fitness. Whew. Okay, so we have the set of linked nodes. In order to insert, since they sort of maintain the order, I don't have to do this shifting thing. I can just say, hey, whatever's currently pointing at front, well, let's just create a new node, point that at whatever front was previously pointing at, and then switch front. So the nodes 4 and 5, totally untouched. Technically, the node 3 was untouched as well. We just sort of inserted this new node in the middle there. So we saved ourselves the shifting, but everything's a separate element, a separate object, and we have to do this sort of puddle jumping thing to get from one to the other. And then we update the number of items. Any questions on that sort of underlying implementation so far? Make it more complex? Oh, yes, please. Who decides the functionality of the ADTs? It is somewhat historical. It was literally Barbara Liskov was like, hey, what are y'all doing? Oh, those are some patterns. I'm going to give some names to it. And now it's sort of colloquial. So it's not like there's like a leader of the ADTs. It's just we all sort of decided on this shared language a while ago and have been using it since the 70s. Yes?
So if I ever, any language use the equivalent of a list, I would assume that it would have like a set, append, delete, remove, that sort of thing.
Yes, great question. So if you, for example, were to go into Python and want to use a list, you can assume that anything with the name list will have the same kind of functionality. The name of the methods might be a little different, which is annoying. Like, for example, in Q, some languages use NQ and DQ, and some languages use add and remove, that kind of thing, but the same general functionality. Yes, please. Yes, you're absolutely right, yeah. Yes, you are so close, and I am so thankful for this question. In fact, this is such a good question. I have a whole slide about it in a few slides, so thank you. Foreshadowing? I don't know. Great. Let's do a few more, and then we're going to talk exactly about this difference between contiguous and non-contiguous memory, which is why sometimes you would pick one over the other. So here, let's do a delete. In this particular case, we want to delete the thing, whatever thing happens to be at index 0. Since I delete that, that means then I can't really leave a gap at the beginning. So again, I'm going to copy things over so I don't lose anything. I'm going to copy the file. Where am I? There we go. We're going to copy, 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 and then I'm going to reduce the size. Now here's something where I still have like an extra copy of 5 hanging out at index 3, but I've reduced my size variable, so I don't care what's stored in there. You don't need to go in and clean it out. It's just kind of like garbage you can ignore. So the size variable sort of gives you this way to dictate what parts of the array are in play, and it doesn't matter what's stored in the ones that are out of play, but that's why the size variable becomes so important. And then, again, with the linked list, if we call delete at index 0, well, then we just skip that node, and we let the garbage collector take it off to wherever magical location it does. So again, we don't have to do the shifting. That's convenient. And we reduce size. Okay. Let's talk about append, but in this case, where we have append, and we've already used up the capacity of our array. So we initially made an array of size 4, and now we want to append a 5th element, but we can't just add a singular space onto an array. That's not how arrays work in Java, partially because of the contiguous memory thing. And so there is a convention that what we generally do is we're trying to balance the cost of creating a new array and individually copying everything over against the cost of unused space. So if in this moment I was like, ooh, I ran out of space, I'm going to make a brand new array with one extra space, because that's all I need, just one extra space, then I would make sure that I pretty much never have any wasted space, but it's going to get really expensive to create another array and then copy everything over. So the convention is to double the size of the array. Go ask some wonderful researchers. That seems to be some magical sort of balance point that we use between the cost of duplicating and copying everything over and not having too much wasted space. But that is a design choice. If you are implementing for, say, mobile phones and you don't have a lot of extra space, maybe you won't double it. If you're working on large computers and you want things to be super fast and you're willing to pay that sort of copy over fee like one time and you have a general idea of when that's going to happen, maybe you really make the array bigger. Linked list, again, delightfully convenient. Okay, great, there we go. Where we just add something new at the end. Now in this particular linked list, I didn't go through the effort of animating, but remember, because in a linked list, each node only knows about its next most neighbor. If I'm trying to append something at this box, I probably have a current pointer that starts at the front and has to be like, okay, 10, are you the back? Keep going. 3, are you the back? Nope. 4, are you the back? Nope. 5, are you the back? Ah, yes, finally. Now I can append. So this is a situation where the linked list is actually incurring that iteration in order for you to append. And that's going to happen regardless of the capacity. Every time you append to the end, you're going to have to loop from the front to get to the back. I'm going to pause here. Questions on this slide? Yes, please, in the back. So the question was, what if you have to append 2 numbers? And I think where your brain is probably going is like, what if I know I had to append 2 numbers? Would be silly to go back to the front and start over every time, right? No, that's what happens. In a singularly linked list, every append call is its own independent thing where you start at the front and you loop all the way into the back. Out of interest, can anybody come up with some maybe ways we could alter the linked list or add some information to these nodes that would save us in that particular example? Yeah.
Yes, I was actually about to ask that. So in what you just described, it seems like the node itself knows if it's the back or not, right? But you can kind of take it one step above and have the list itself have like a field for back and just the address of which node, or maybe not the address, but actually know the address of which node is the back, and then you just reference that, go to that, and then append to that, right? And just update the back pointer.
Yes, I love what you said because you also added a level of abstraction here. And so what's happening in the linked list scenario is we actually have a linked list, which is an object that is a collection of list node objects. So you're right, the way that we know this is the back, if the only fields the list node has available to itself is like the value and the next field, then we just have to loop until that next field is null, because that's all it knows. But what if we lift that information up one abstraction level to the linked list object, and instead of having just a singular field, which is the front pointer to the very first node, we could add another field. We could say, hey, let's have a back pointer too, and always maintain to the back. There are other examples of how to make this even more efficient. I don't suppose anybody has any other great ideas, because we can make whatever we want out of these list nodes. They can store as much information as they would like. Yeah, sure, in the back. Yes, thank you. So there's also this concept of something called doubly linked lists, which you may not have seen from intro, where each of these individual list nodes, instead of only storing the value and the next field, what if they stored the value and the next field and also the previous field, so that you can go bi-directionally up and down the linked list? That's really convenient and probably saves me some of that moving around. But when hopefully you did that linked list problem in intro and we all went crazy from the null pointer sections, you think you were having a bad time then, try programming with doubly linked lists. You're going to go absolutely insane with double pointers. So again, our trade-off in that case is, yes, absolutely more convenient, but we are increasing the size of memory that each node stores And we're going to increase the amount of work we have to do anytime we change something, because now we don't just have to update the next pointer, we also have to update the previous pointer. So linked lists are fun because they're really flexible. We can decide how much information each node stores, and it's up to us to balance how complicated the node is, how much information the node stores, with how convenient we want the structure to be. Okay, great. Okay, let's talk math. Yay! So you may have heard of something called Big O. I think it was touched briefly in intro. I am going to be very direct with you. We are going to talk about it constantly in this class. And once upon a time, I used to make you do math proofs in this class, but some very wise person was like, Casey, there's no need for that. So I will not make you write mathematical proofs anymore. But you should be aware that I am going to expect you to sort of know the relative rates of growth of some of these classes. So what the Big O complexity is it is a way for us to measure how many extra instructions are going to get executed by your code as the amount of information we store in it grows. So, for example, if I have something that's in the constant complexity class, that might be something like, oh, I want to get an item at an element, like at an index of an array. If the array holds 5 items and I'm getting something at index 2, that takes like 1 cycle. I just say, hey, at index 2, give me that thing. It doesn't matter if that array had 5 items or 500 items. It takes the same amount of time. It's constant. It's independent of how many things are stored in the array. Doesn't matter. Big, small, same time, constant. That's the ideal. We're always trying to get to that. That's the fastest. Then we have logarithmic growth, where it's kind of like expensive in the beginning, but it sort of levels out. That's that binary search, the telephone book one. Like in the very beginning, when we look in the middle, we sort of divide it in half, and it's like we eliminate half of the possibilities. That's like really satisfying. But as we kind of like flip half and half again, the amount we're reducing shrinks in size. And so we end up with this sort of like it starts fast and then levels out. That's down here. It's also a really nice growth rate, because what that means is that as the amount of things we're searching expands, well, even as things start to get really, really big, the difference between those bigger numbers starts to shrink in the amount of time it takes us to find the thing we're looking for. Then we have what might be a little bit easier for our brains to understand, which is linear. That is directly related to how many things are stored in the data structure, how long it takes. All that stuff we were doing with arrays, where we had to like shift everything over, that's linear. Because if we had to shift everything in the array and there was 4 things, that meant there were 3 shifts and an insert. Then imagine if you had to do that same thing for an array of 300. It's going to take a lot longer. But the amount of time longer it'll loop to do that is directly proportionate to how many things are stored in the array. I'm going to get into all of these in excruciating detail, but this is the way we want to start thinking about how we evaluate the effectiveness of our code. How many more instructions, how many more actions are we going to have to take in order to accomplish what we want? And how does that number of actions change as the size of data we're working with starts to get bigger and bigger and bigger? Okay, great. I want to get to that wonderful slide. Oh, this is talking about Big O. Hang on. We're going to, there we go. We're going to finish this off because I promised I would talk about this. So one other thing to consider in the design trade-offs is this idea of contiguous versus non-contiguous memory. Spoiler alert, the way that your computer stores anything is an array. That's why we're kind of obsessed with arrays. Your RAM is just a big array. Your hard disk is just a big array. And what that means is your computer memory is just a bunch of spaces with addresses. Now, contiguous memory is if I say, hey, computer, I need like 10 things that are going to be stored related to one another. That's an array. The computer will go and find 10 things right next to each other. So when I do that looping, it's actually really fast in memory to be like, oh, look at my neighbor in memory. Different from if I have the linked list situation, there's the contiguous, where maybe a node stored there in memory, and then the next node is stored there in memory, and the next node is stored there in memory, because the computer only knows how much memory to set aside whenever you use the keyword new. So linked lists might kind of be stored all over your computer memory. And so even though the big O to loop from the front to the end of each of these would be linear, it's going to take longer on the linked list because we're jumping around in memory. Okay, I'm going to leave it there. We're going to do those fun design decisions on Monday, and we're going to talk about some other ADTs as well. Keep an eye out for that post on the Ed board. I'll share the homework assignment. Have a great weekend.